All right. Hello, everybody. Welcome back to Comp 3430 Operating Systems. It's our last class. Yeah. Hooray. Yeah. You shouldn't all be so excited to not see me again for the rest of the summer. No more weeks. No more weeks. No more weeks. Okay. So yes, this stuff. What I want us to be able to do by the end of today is really paging. That's the focus that I want to have for today. And it's kind of related directly to all the virtual memory stuff that we've done up until this point. So in addition to what we've been thinking about with virtual memory for base and bounds and for segmentation, I want us to be able to describe how the operating system works with the underlying hardware to manage paging specifically. And then I want you to be able to describe some of the data structures and approaches that are used to manage a partitioning strategy such as paging. Algorithms, really there aren't actually any major algorithms that are used for paging, because the places where we would have needed algorithms, like compacting garbage collector sort of thing, is solved by paging. And in fact, we're really just using a bunch of data structures to help resolve the issue of you have to spend a bunch of time doing extra stuff. And so we'll spend some time thinking about paging, and we'll spend some time taking a look at the data structures that are used by an operating system to do paging. And then finally, what I want us to be able to do is to take this idea of paging and page tables and start to make connections to file systems. So this is going to take us kind of full circle here. Effectively, we're going to start thinking about memory as a file system itself, where we don't have to worry too much about things like the rotational delay of a disk because it's fast, it's memory, it's going to be random access, and all access times are constant regardless of where it is, as far as we're concerned with an operating system. Before we get to any of that, though, I wanted to give you an opportunity to ask some questions about the final exam. So I'll give you a moment to get connected to this. And then I'm going to switch over to a slide that'll give us a brief description of some of the things that you can expect about the final exam. Okay, I'm going to switch to my slides. I'll let you ask your questions, but I'm going to tell you a little bit about the exam first. So our exam is 1 week from today. It's next Thursday. It's going to be an E2 105, which I think is across the hall. No, it's down the hall. It's at the other end of the hallway. I don't know why it's not in this room, but it is what it is. This is a link to the final exam schedule, so you can take a look at it there if you want to. The exam's going to be 2 hours, so we'll have 2 hours on the wall for doing the final exam. Just like the term test, the seating's going to be assigned. You can expect me to send you an email on the morning of Thursday saying this is what your seat number is, and I'll put up a map of the room up on the course webpage and in the email that I send to you so you have a sense of where your seat is going to be when you get here. But I'll also bring an electronic copy of the seat assignments so that we can look it up quickly if we need to. The material that you can expect to be on the exam is going to be cumulative from the beginning of the course. So this is a final comprehensive exam. So there's going to be stuff that's from earlier in the course that you can expect to show up on this final exam, in addition to the material that we have after the term test. However, the emphasis will be on stuff after the term test. You have not yet been assessed on stuff after the term test, so that's where most of the points are going to be allocated for the final exam. Structurally, it's going to be similar to the term test. So in terms of the types of questions, the types of responses, you can look back to the way that the term test looks to get a sense of what you should expect to see on the final exam. And as with the term test, there's no programming in C. I'm not going to ask you to write C code. I'm not going to ask you to memorize function signatures. I might ask you to write pseudocode. I might ask you to interpret and read C code, but I'm not going to ask you to write C code that has to be syntactically valid code. So in terms of pseudocode, it would be similar to what I was thinking about for the term test. You know that the word fork is responsible for causing a process to start. You know that exec is a word that's related to starting a new program from a process. You know that the word wait means that you should stop in a parent process and wait for that process to end. But I don't actually care about you being able to know with great detail what the arguments of these things are supposed to be, or what the order of arguments, or what the actual function name even is, just as long as it's clear what you're referring to in that thing. As with the term test, I'm going to post a news item on the course webpage that lists the learning outcomes and their relative weights in advance of the final exam. I'm going to do my very best to do that by the end of the day tomorrow. I can't promise that I'm going to be able to do that, but I'm going to do my very best to get that by the end of the day tomorrow, and for sure by Monday, at the end of the day on Monday, to give you a little bit of guidance on how to focus your efforts when preparing for the final exam. This is up on the course webpage, so you can find this on the course webpage if you want to be able to find it. So I'm going to pop over to the questions. How much emphasis is going to be on the second half of the course? I mean, I haven't fully prepared the final exam yet, so I'm going to say that this estimate, 65% and 35%, is probably a reasonable estimate of how much to expect on each part of the material. One thing that you can almost expect a little bit is that there might be kinds of questions that will like mix some ideas from different parts of the course. Do I need to refresh the page, or is there actually only one question? I'm going to refresh the page just in case. Oh, there's another question. I'm still refreshing the page. Hints, please. Okay. I mean, hints, I guess, are going to be more like strategy hints. I'd say take a look back at the term test to get a sense of not just the types of questions that are there, but look at the grading guide that I posted to get a sense of like what kinds of things you could expect. This is going to be both for the test that you wrote, but also for the sample test that I posted from the last term. Those would be good places to get a sense, but the emphasis is really on the learning outcomes. So I'm looking for you to demonstrate your ability to do a learning outcome. That's what I'm really trying to assess on these final exams and all on tests. So focus on that. Will there be stuff on the exam that was only talked about in the required sections for the textbook? So that's possible. Again, I'm going to put the learning outcomes that I'm actually including on the test up on the course webpage. And if you look at the course schedule, I've tried to make it clear which chapter the learning outcomes are described in. Some of them and a lot of them were described in class, but there are some that were described in our textbook and not something that we talked about in class. But it's possible that that will happen. But again, I haven't finished preparing the final exam, so I can't say for sure if that's going to be there. So I'm going to point at the statements again of it's about the learning outcomes. So I'm really not looking for trivia. Memorizing stuff is maybe not an ideal strategy for this. I'm not looking for you to like describe to me or provide definitions for me. I'm not really looking for you to provide definitions of stuff for me. So knowing stuff from the knowing how much stuff from the textbook do you need to know? High-level concepts are the big thing, and how those high-level concepts relate to each other is what is really important to me in terms of what I'm going to assess you on in the final exam. Can I provide a sample final? So I don't have a sample final to give you. I don't want to give you the final exam that I used for the last term because I'm going to reuse parts of that for this term. But I am going to again emphasize that the structure of the final exam will be very similar to what you saw in the term test, and you can kind of use that as a guide for what it will look like. Yeah.
On the midterm, I was a little bit surprised by the amount that I yapped on certain questions, and I happened to get the points that you were looking for.
Yes. Yes.
I thought I had well overreacted, if that makes sense. So I thought I had provided more than actually what you were looking for, but it just turns out that I happened to get almost all of what you were looking for. So there was a discrepancy in what I understood you were looking for versus what you were actually looking for.
Yeah.
So okay. So now on the final exam, I assume the questions will again be somewhat similar with the outcomes posted, and then we'll have to hope that we get it all again.
I mean, I guess you can reflect on what you over-yapped about compared to what I was expecting on the test, and reflect on like I don't have the context here about what you've over-explained versus what I was expecting. So all I can really say is to take a look back at the grading guide and kind of do some self-reflection and decide like how far in depth did I go versus what I was actually thinking about, what me was actually thinking about. Yeah. Again, the sample, I would say, in terms of structure, is going to be best looking at the term test that I've given you. I guess some other places that you could look for additional kinds of questions would be in the textbook summary, the reading notes that I provided. There's a lot of questions that I'll just dump into those and then not really answer them because I don't have answers to them necessarily at the time. But there's also stuff that I'm just thinking about in terms of like what the authors are writing. So that might be another place to get some practice material. If I were a question on the final exam, I would describe myself as, I don't know, thought-provoking. Yeah. Again, learning outcomes. I gotta point back at learning outcomes, and I have to just like keep emphatically gesturing at learning outcomes. Those are really what I want from these questions. I want you to demonstrate learning outcomes. And so, if I go back to what we've got for today, like one of them is I want you to be able to discuss the benefits of partitioning memory and address spaces and compare and contrast methods for address translation. And so I'm looking for you to be able to tell me a little bit about like in today's context, how does paging fix the problems that we encountered with segmentation? What were the problems, and then what does paging do that solves those problems? What problems was there with base and bounds, and how does segmentation solve the problems with base and bounds? So those are the kinds of things that I'm thinking about in terms of being able to demonstrate these learning outcomes. Explain how a process's entire address space can be provided via the support of provided or supported via the concept of virtual memory. This one is like a high-level description. We've got these mega-size virtual address spaces, and physical memory is only so big. So how does it work? Like describing how we can actually cram all of this stuff in. And the best answer really is you just don't allocate everything. You just allocate what you're going to be using for this thing. Describing how the OS works with underlying hardware, and then operating system data structures. So this is thinking about things like how the process control block is affected when we're doing virtual memory for processes. So with base and bounds, it's like one set of registers. With segmentation, it's 2 or 3 sets of registers. And then with paging, as we'll see today, it's a table structure that we're embedding in our process control block. So learning outcomes. So again, I guess I'd say taking a look at the reading notes that I provided, because there are some questions there. Someone suggested to me the idea of using ChatGPT to generate questions, and I think that might be reasonable. I think that might be a reasonable way to ask ChatGPT is like, given this learning outcome, make a question. It's not going to sound like the question I'm writing, obviously, because I don't really think that I chat like ChatGPT, but that might be another way to do that. Okay. I don't know how to respond to that, but okay. When I'm writing the exam, I try to make sure that I'm not being tricky. My goal is not actually to trick you. I don't have a goal to trick you. It's going to be a mixture of both. In some cases, what we do in class is like, I'm doing a high-level overview of the material that's in the textbook, and then the textbook is giving you a much deeper dive about what's actually going on underneath this stuff. So with the page table stuff, like I'm going to draw a picture and we're going to talk a little bit about it, but the textbook does a much more thorough job of describing those ideas. Yeah, and it might work if I'd actually finished making the exam already. I mean, almost all of my final exams and almost all of my tests have a bonus question that is shaped like this, so you could expect something like this. I don't know if it'll be Walter that I'll ask you to draw, but probably something. As I mentioned before, that's like the little treat that I get for myself after grading the exam. So like I said, I'm going to try to put the set of learning outcomes that actually appear on the final exam to help guide you in your preparation for the final exam so that you don't have to necessarily look at breadth. Even before that, though, one thing that I would suggest is to take a look at the learning outcomes that were already on the term test. Those are much less likely to show up on the final exam because I've already asked you those questions. So I'm not likely to ask you them again. I'm not promising that I won't, but they're so much less likely to show up. And even if they did show up, they would be emphasized much, much less than other stuff that I haven't actually assessed you on yet. What's my favorite piece of the Linux kernel source? I don't think I have a favorite piece. I just love Tux as a mascot. That's not really a piece of kernel source code, but it's something related to that. Again, I'm really sorry, but I can't say because I haven't finished preparing it yet. You can kind of expect that the final exam will be relative in size to what the term test was. The term test was a 75-minute term test, and this is a 2-hour final exam, so you can expect it to be relative in size to that one. Okay. And then I think that's it. All right, awesome. I thought about making this like a streaming text thing, but I was deeply worried that there would be just like people swearing about the new transit plan if I did this. I'll give you like 30 more seconds. It's pretty flat. I mean, there is a big bump at the it's made worse. I suppose I should vote for this question myself. Nine one four seven. There. It has made my commute so much nicer. Again, I only have to take one bus, and I feel terrible if it's making your commute much worse, but this means that I can check out on the bus and read a book in the winter instead of driving. I don't really like driving here. I'd much rather take the bus. All right. So I am going to come back to this Mentimeter later in class, time permitting, because I have a bunch of review questions. So that would be another place to get some ideas for where to look for stuff. But let's talk about paging. So base and bounds is our first approach to implementing virtual memory. And the basic idea with base and bounds is that I want to partition physical memory, and I'm going to make my virtual address space much, much smaller so that it actually fits into these partitions. That was fine because it's a pretty simple approach to virtual memory. I only have to add really 2 things to my process control block, and even then, it's really only one thing that I need to add to my process control block, which is where is the address space in main memory for this process? The problem with it is that once we've done that partitioning of main memory, we have a fixed number of tasks. We could solve this by using an approach called swapping, but we're not going to talk about swapping. Swapping, the idea is I'm just going to take the thing that's not currently being used and push it down into my hard drive because it's not currently being used, and then put it back into main memory when I do need to use it. Based on what we saw in this, though, it's really just a fixed number of tasks, and that's not great. That's not an ideal solution here. The other problem that we saw with base and bounds was this idea of internal fragmentation. Once I've allocated one partition of main memory to this process, it never uses that middle part of its address space. Almost never uses that middle part of its address space. And so there's a bunch of space that's wasted, and it's been allocated to a process, and it's not usable by anything else, even if it's not used by that process. Segmentation was our next approach, and segmentation is good because it's effectively made it so that we can have an arbitrary number of tasks, many more tasks than we could have had with the base and bounds approach. Because we're only allocating as much of each part of our address space as we are currently using in the process. So I'm not allocating that big part in the middle. I'm only going to take my code heap section and my stack section, and I'm going to only allocate in main memory as much as I'm currently actually using of those things. So all the space that was allocated and unusable in base and bounds is just not allocated now, and so it's usable by other processes, and so I can fit more tasks into this thing. But the problem with this is that we don't fix the size of the allocation that we're making. They grow and they shrink. Because they're varying in size, we can run into a situation where there might be overall enough free space in main memory to put more things, but it's not contiguous. And so I would have to do things like garbage collection, or I would have to do things like compacting main memory, so squishing everything to the top so I have a bigger chunk of contiguous free memory to be able to do this. Like base and bounds, this approach was pretty simple in terms of what we needed to add to our process control block. Where base and bounds is, I need to have a base register and a bounds register. Segmentation is, I need to have a base and a bounds register for each of the segments that I'm allocating for these processes. So it's still quite simple, and it's still minimal in terms of the amount of space and stuff that we need to do for this. But external fragmentation ultimately makes this a no-go. It's going to take so much time to free up extra space when it's necessary to free up extra space that is just going to make this not work very well. And so if partitioning memory in the first place allowed us to have virtual address spaces put into main memory, and then if partitioning the address space allowed us to have more processes running at the same time, paging is taking this idea and doing it to both main memory and our address space. Let's partition memory instead of just partitioning one or the other. I'm going to partition my physical memory into page frames. So physical memory here is I've got 32 gigabytes of RAM on my laptop, and I'm going to partition that 32 gigabytes of space into page frames. Frames here are like, I'm going to stick the pages into the frames. These are going to actually go into the physical location in main memory. And I'm going to partition my virtual address space into pages. Both page frames and pages are equal in size. So the size of a page frame is equal to the size of a page, because effectively what I want to do is have a virtual address space for a process where we're going to allocate pages in that virtual address space, and we're just going to stuff them into page frames in physical memory. Let's draw this idea out. So I'm going to pop over here to my tablet, and what I want to draw here is we've got physical memory over here, and we've got an address space, a virtual address space over here. I'm going to draw both of these in the same way. The traditional rectangle. Physical memory here, we're going to talk about this as though it's my laptop. So physical memory is going to have 32 gigabytes of space to work with. And our virtual address space for our running process will also be the traditional rectangle shape. but it's going to have, and we're just kind of hand waving this, 64 bits of space. So it's still the same idea. We have these address spaces that are just much bigger than it can possibly fit into the actual physical space that we have. But the difference now is that I'm going to take my physical memory and I'm going to partition physical memory into page frames. I'm going to take this physical memory and I'm going to partition it into 4 kilobyte size chunks. Typically, it's 4 kilobytes that we have for pages. Each page frame in main memory will have a page frame number, and I'm going to mark these page frame numbers as n plus 1, n plus 2, n plus 3, plus 4, plus 5, plus 6, plus 7. In my virtual address space, I'm going to have the things that we would expect to have in a virtual address space. I'm going to have a code section. I'm going to mark that as up here. We're going to have a heap. And we're going to have a stack way down here. I'm going to take my virtual address space, and I'm also going to partition that. I want to emphasize that these are not to scale. These are not to scale. 64 gigabytes of space, 64 bits of gigabytes of space is just, it's too big to drop, but it's not to scale. The idea is I want to take my virtual address space, and I want to split that up into pages. And I'm going to mark these as page M, M plus 1, plus 2, plus 3, plus 4, plus 5, plus 6, plus 7. And within the virtual address space, we're going to have things like our stack and our code and our heap. I'm going to say here that my stack takes up pages up to maybe partway through M here. So we're going to say that right now our virtual address space has a stack, and the pages for this stack are allocated up to about this point. So they're halfway allocated through one entire page. The pages are not really kind of lying out here in space. They're literally put into main memory directly, into the page frames that we have in main memory. So that means things like page M plus 1 here is going to be allocated to page frame N plus 5. And page M plus 4 might be allocated to page frame N plus 1. Each page will go into a different page frame somewhere in physical memory. Page M, we're going to say, is here in page plus 7. It's only going to be allocated to the kind of halfway point here. And these other ones that we've got will be allocated fully. The way that we can kind of think about this is that we'll take this and we're going to turn it horizontal and pretend that it's a hard drive or a volume. With our volumes, we had blocks. All the blocks were 4 kilobytes in size, and we were able to put files into those blocks, the data for the files into those blocks. Effectively, what we're doing here is taking main memory and treating it as though it is a set of uniform size blocks. Now I'm going to take the virtual address space and I'm actually going to write those pages from the virtual address space into the page frames that we have in physical memory here. The way that our operating system is going to have to work with this structure is that in the process control block for the process, we're going to have a page table. Page table is going to be the mapping between the virtual address, the virtual page number, and the physical page frame where that thing is stored. So in the case that we've got here, we're going to have a table that looks kind of like this. I've got physical frame numbers and virtual page numbers. In this table, I'm going to have entries here that represent the allocations that I've got. So page M in my virtual address space is going to page N plus 7. Page frame N plus 7. Virtual page number M plus 1 is going to page frame N plus 5, and page number M is going up to, I'm sorry, M plus 4 is going up to page N plus 1. It's not going to be dumped here in this arbitrary order that I've got. It's a table. It's going to be an array. It's going to be an array that represents the mappings between the virtual addresses and the physical page frames that we've got. The way that we set this page table up is not just going to be an arbitrary operating system specific thing, but instead the structure of this page table will be defined, structure is defined by hardware. And so Intel publishes a 5,000 page PDF document, and I'm not exaggerating here, it's 5,000 plus pages long, that describe things like the structure that the page table has to be in so that the operating system can tell the hardware where to find the page table mapping. This is the structure of each page table entry in detail. This is what all the bytes should be for this thing. Our operating system is going to have to keep track of all of the allocations of virtual page numbers to physical frame numbers. And it's also going to have to keep track of, for the hardware, where does the page table start in memory? Our page table here is part of the process control block. And so that means that the page table itself is going to be put into page frames in physical memory for this process. The page table is in memory, the virtual address space is in physical memory, everything is in physical memory here. But this is great because all of the pages are fixed in size. Every page is the same size. And just like we had with file systems, if I want to find a free block with a file system, I just look at the allocation structure and it tells me this block is free. If I need to make my stack bigger here, I just find another page frame that's not currently being used. If I want to make the heap bigger, I just find another page frame that's not currently being used. I don't have to find one that's big enough. I just find one that's free, and then I use that one for that thing that I'm currently trying to allocate here. It also means that we still do have some internal fragmentation. We've reintroduced this idea because we can have page frames that are partly allocated to a process, but it doesn't matter. They're 4 kilobytes in size. In the same way that when we had terabyte-sized disks with 4 kilobyte-sized blocks, it doesn't matter if I lose 4K because I have a huge amount of space here. I don't really care that much. And so I've eliminated external fragmentation by having all of my pages and page frames be exactly the same size, and I've effectively minimized internal fragmentation. So internal fragmentation still exists. But I've minimized it. I've sliced this so thin that it becomes irrelevant. It doesn't matter that I'm wasting 3096 bytes. I don't care. I really don't care in the context of 32 gigabytes of physical memory. Any questions about this? We doing okay so far? Okay. Paging is great. Paging's really good. I've eliminated external fragmentation. With segmentation, my segments were varying in size. And so I had to find enough free space somewhere to put a new segment, or I had to find enough free space to expand an existing segment if it was possible. There might have been enough space around for me to actually put this in total, but I still had to make that space available. With paging, I don't have that problem. I just find a free page and I'm good. If there's no free pages, then I'm out of memory. I don't have any memory left to allocate. If I have a free page, I can use it and I can just take it and I can use allocation structures to do that. I've minimized internal fragmentation. It came back, but it doesn't matter because the amount of space that I'm losing to internal fragmentation is so small that it's irrelevant. I haven't allocated this giant chunk of my virtual address space anymore. I'm still only allocating as much as I'm using in the virtual address space. So I'm only allocating the part of the code segment that I'm actually using. I'm only allocating the heap that I'm actually using. I'm only allocating the stack that I'm actually using. I've minimized internal fragmentation, and so it doesn't really matter anymore. But the problem with this is that it's going to suffer from some speed and size issues. The speed issues are that the page tables are in memory. And so remember back to thinking about, well, what does the OS do and what does the hardware do in terms of translating addresses? If the OS were doing it, we'd have to do things like having instructions running that are translating the program counter's virtual address into a physical address, and then having to translate the address of the operands for the instructions. We've reintroduced those problems here. I now, as an operating system, can tell the hardware, hey, the page table starts here. But now the hardware needs to go to memory to find the translations for each of the page numbers that it's looking at for this process that's currently running. And so for each lookup, it's going to have to go back to main memory and get the translation, and then go back to running instructions, and then go back to main memory to get more translations as necessary. This is something that's solved with caching. The structure that's part of hardware that does this is called the translation look-aside buffer. And you can just imagine that this is a fast place for us to keep these translations close to the processor so that we don't always have to go back to physical memory to get the translations. End of discussion about this. In computer organization in Comp 3370, you will spend time thinking about this idea of caching instructions, caching translations. If you've done Comp 3370 already, you've thought about these things already, and I'm not going to talk about them because they fit more into that course than they do in this course. There's a chapter in our textbook about this concept, but I'm not going to talk about it. The other problem is that there are size issues with this approach. Size in terms of the amount of memory that's needed to do this. Let's do some calculations for a 64-bit address space with 4 kilobyte size pages. So to do the translation, I'm going to need to calculate the total number I want to calculate the total number of pages in my virtual address space. With paging as it is right now, I need to have an entry in my page table for every page in virtual memory. Some of them are going to be marked as unallocated. So here, if my page table goes to m+5 here, I'm going to have an entry here that just says it's not allocated. If a process tries to read that page fault, segmentation fault, we will get a segmentation fault from this because it's not currently allocated to this process. But this table now has to have an entry in it for every single page, whether it's allocated or not. And so to get to that point, I'm going to calculate this as there are going to be 2 to the 64 possible pages, 2 to the 64 possible addresses, but I'm dividing this address space into 4 kilobyte size chunks. So I'm going to say 2 to the 64 minus log base 2 of 4096 or 4K. This should be the number of pages that I have in my main memory. I'm going to say that it would be reasonable for the size of a page table entry to be 8 bytes. I can't do this in my head, so I'm clearly looking at my tablet to write this number out. This is 3.6 times 10 to the 16 bytes for the page table, which is about 3355432 gigabytes. I don't think it's going to fit. I don't think it's going to fit in main memory anymore. I don't think it's going to fit. Oh no, oh no. The size of a page table, as we've implemented it here, is not manageable for 64-bit address spaces. It's not manageable for 32-bit address spaces. It's not manageable for anything that's bigger than like trivially small sizes of virtual address spaces. Most of the address space that's in that virtual address space are not allocated by the process. If I go back to my diagram here, we still have internal fragmentation of the address space. Most of the space here is not allocated for use by the process, and so our page table will mostly be filled with blanks. This is not allocated, this one's not allocated, this one's not allocated, and many, many, many millions of gigabytes of this is not allocated right now by this process. So what we've effectively done is taken internal fragmentation out of our address space, and we've just moved it to the page table itself. The page table has to have allocations for these pages that are not allocated by the process. And so I've got the same problem that we originally started with, base and bounds, but it's no longer the address space that's internally fragmented, it's the page table itself. And so we can address this problem with a different data structure that's called a page directory. When we got to paging in the first place, we were starting to apply this idea of partitioning both virtual addresses, virtual address space, and our physical memory. And that solved external fragmentation by making all the pages the same size. We don't have to find a space that's big enough. We just have to find something that is free, and we've minimized internal fragmentation. And so the idea of a page directory is effectively, if partitioning worked well for the virtual address space and it worked well for main memory, let's partition the page table itself. Let's talk about file systems. Paging and file systems are pretty different problems. I think they're pretty different problems, but they're kind of like going to structurally look similar to each other in the end. Both of these things are at different levels of that memory hierarchy that we were talking about, where one is more like for persistent storage and the other one is for fast but ephemeral or volatile storage. When we were thinking about ext2 and VSFS, we had a lot of metadata that appeared at the very beginning of the volume. There was information about the volume itself and the superblock. There were some allocation structures that described things like which inodes are currently in use in this inode bitmap and which data blocks are currently in use in this data bitmap. Then we had information about the files themselves in these inodes. So this was describing things like how big the file is, and importantly, where to find the data for the file in the form of direct and indirect block pointers. And then in the data region itself, we had the actual data for files, we had metadata for directories, and we had blocks that contained block pointers themselves. So our inode might point at a block itself that says, these are where more block pointers are for this file. These are where you can find the rest of the file's contents once it gets big enough. Our indirect block pointer structure looked a little bit like this, where we were taking direct block pointers, we filled these up, and then we started pointing at indirect blocks where the blocks themselves would be containing block pointers. A page directory is effectively doing the same thing. Effectively, what we're saying here is we're going to take this linear page table that we've got. So this is what we had right now with paging. I'm going to take this linear page table that I've got, and I'm going to break that up into smaller pieces. I'm going to add indirection to this. I'm going to partition this. And instead of having direct pointers to the pages and the page frame, between the pages and the page frames, I'm going to have a pointer that points at a page that's full of page table entries. But I'm only going to allocate the page of page table entries if the page itself is allocated by the process. So I don't really like this picture. I like our textbook a lot, but I don't like the way that they've described this idea in terms of page directories. And so I'd like to draw you a different picture for page directories. I'm going to pop back to my tablet here. And what I want to do is I want to start by thinking about what our page table actually looks like. So I'm going to draw the traditional rectangle shape. But this time I'm not trying to represent physical memory, and I'm not trying to represent virtual address space, but instead what I'm trying to represent is the page table. With a linear page table, we're going to have virtual page numbers and physical frame numbers where those things are located. This would go off to whatever 3 million gigabytes it was to take up the entire address space for the process that we've got. The structure that this is going to look like is I'm going to have entry 00, 01, 02, 03, 04, 05, 06, 7, 8, 9, 10, 11, ... These are my virtual page numbers in my virtual address space. And these are going to be things like, this is the code section. And this is my heap. And then way down here at the bottom somewhere would start to be the pages that represent my stack. In my page table here, what I'm going to have are page frame numbers for each of the pages that's in my address space. So I'm going to say that this is going into page 15. This one goes into page 37. This one goes into page 2. This one is page 5. And then ... So this is the same structure that we have right now. This is our linear page table here. But once we get past the heap, all of these entries are just blank. These have not actually been allocated by the process. The basic idea of a page directory is that I'm going to take that page table that I've got there, and I'm going to partition it in the same way that I partitioned physical memory and in the same way that I partitioned my virtual address space. I'm going to simplify this, and I'm going to say that we're going to take the first digit of this number, and that's how we're going to partition this address space with this page table itself. So my page directory is going to consist of a mapping of a VPN prefix. And so this is going to be for all pages that start with 0. This is going to be for all pages that start with 1. This is going to be for all pages that start with 2 and 3 and 4 and 5 and 6 and so on. And what I'm going to say is that to find the page table entries for virtual page numbers that start with 0, you need to go to, let's say, page AB. So this will be the physical frame number. This will be the actual page, this actual 4 kilobyte block in main memory that's filled with page table entries now. And all of these page table entries are going to be the ones that start with 0. So in terms of what we've got in our current virtual address space here, we're going to take these entries here that have actually been allocated, the ones that have a prefix of 0, and we're going to just put those in a different page all by themselves. So 0, 0 is 1, 5, and then 3, 7, and then 2, and then 5, and then ... And so this will still continue to be things like our code section and our heap. But in this page table, I didn't allocate anything for pages that start with 1. And I didn't allocate anything for pages that start with 2. And I didn't allocate anything for pages that start with 3. So my page directory structure here itself can still be filled with blanks for these ones. And I don't need to allocate the pages that have all of the translations for the ones that start with 1 because they weren't allocated by the process. So I've taken this part of my page table here, and I've eliminated having to allocate page table entries for that because there's nothing in there that's been allocated by the process. So our code in our heap section here These are all virtual page numbers that start with 00, 01, 02, 03. I'm partitioning this page table based on the prefixes that I have for this. And I'm using that prefix as an index into my directory. And I'm only going to actually have pages allocated for page numbers that have been allocated by the process itself. This means that I don't have to allocate anything for all of these ones. And I don't have to allocate anything for the ones that have a prefix of 1 and a prefix of 2 and a prefix of 3 because the process never actually used those things. Are we okay with this idea? Yes.
Page directory with the AD. It's basically saying, okay, so you basically go there and say the ones with prefix 0, it has some stuff in it. So we want to go to that memory location in physical memory AD.
Yeah.
And in that physical memory AD, you find all the different things in there that correspond to the actual pages of the data.
Yes. Yes. So the idea for translation, the process for translation would effectively be in the hardware. I have a virtual address of 01. The virtual address of 01, if I'm working with a page table, I just go to that entry in the page table and just find the direct mapping. With a page directory, if I get a virtual address that's 01, I'm going to start by looking at the page directory itself with the prefix of 0 to find the physical frame number that has all of the direct mappings for virtual page numbers that start with 0. Once I get to that point, then I'm able to say, now I can look for the one that is 01 here and see that it is in physical frame number 37, and then go to that to actually find the data for that thing. Yes? Every process would have its own page directory, yes.
And then, since we still have, or we subdivided our memory into these page
Frames. Yeah.
Would we then not be able to ever allocate all of them because it would still take unboundable numbers of gigabytes to allocate every page frame? We still need the data to do the mapping regardless of it.
You're right. It's still going to take a lot of space to do this mapping, but what we're taking advantage of is the fact that most of the space in the virtual address space is not allocated by the process in the first place. If I'm using a 4-bit prefix here, then my page directory is 16 entries long, and that's it. And that might mean that I'm only allocating of those 16 entries, like 4 of them. The rest of them would be dashes or blanks like this. They're not actually allocated by the process. The ones at the top might be allocated, the one at the bottom might be allocated for the stack. If I'm using 4 bits, it's 16 entries. If I'm using 8 bits, it's a lot more. It's more, but it's still reasonable. It's not many millions of gigabytes anymore. Yeah.
Where we also segmented the virtual space into page numbers as well.
Yes. So everything is partitioned here. Virtual memory and physical memory are both partitioned. Yeah.
Okay, so you base it off of the prefix, the first number of the peak. Wouldn't you have a ton of entries though? So like into the millions probably, or at least thousands, right? So there's going to be a lot more than just 10 entries that start with 1. You're going to have all the 100s, the 1,000, the 100,000, the 10,000.
simplifying this a lot, and I'm using decimal here, which is not really the way that we're going to do prefix partitioning. We're going to do prefix partitioning based on the addresses, and we're just going to slice bits off the top. So the most significant 4 bits are going to be used as this is the partition number that we're using in the page directory itself.
Okay, so then my follow-up question may be negative, but which numbers would be prefixed with 0 other than, I guess, the first 10, or technically, arguably, not even those? I guess based on address space.
So our address space, like, it's going to have addresses that are 64 bits long, right? I'm going to change this to be, let's do 8-bit addressing. Let's think about this in terms of 8-bit addressing. So with 8-bit addressing, we're going to have addresses that start at 0, 1, 1, 0, 1, 1, 1, 0, 0, and so on. If I'm allocating 4 bits as the prefix, there are going to be 16 total addresses that start with 0. The 16 total addresses that start with 0, I'm pointing at my screen here. The 16 total addresses that start with 0 would be put into this page if they're allocated. If they're not actually allocated by the process, so if we get down to the point of the pages that start with a prefix of 1, if those ones are not actually allocated, we're just going to put a dash in our page directory entry to say this is not allocated by the process. Any address that starts with this prefix is not allocated. Yeah.
Page numbers 0, like 0, 7, 0, 8, 0, 9, are they allocated in the AB case?
In this case here, I'm going to say that they are not allocated. So there might be pages within this part here that are still having the blank entry as being not allocated. There's a partially allocated page of translations. It doesn't necessarily have to be full. Yeah. Yeah. Binary to hex? Oh gosh, no. I can barely do that in my head. And I don't really want to have you wasting time writing out the translation tables for hex to binary. No. Yeah.
All you need is one single entry for the to be marked as used for you to create that table, correct?
Yes. So if in this case, we're going to say that these ones are not used. So anything up to that point is not used, and only this one is used. Only this one is allocated. Then we would allocate an entire page for translations. And we still have internal fragmentation here because that whole page is going to be allocated for translations. But that's okay because we're minimizing internal fragmentation here because all the pages are the same size and they're quite small. So I don't have to worry too much about having wasted space because not that much space is going to be wasted. Yeah. Yeah.
This is probably in the weeds, but anytime you do a malloc in C, you're grabbing a page of sorts, right? Even if it's 1 byte. And so
Yes.
you're quickly eating up a ton of these sections. Almost a bit of wasted space.
We're working on this order of pages now, though. So if you allocate anything less than 4 kilobytes, you're only going to allocate 1 page. So you're right that if I do this same structure here, if I only allocate this one address, then I'm going to allocate an entire page for that. But the next time you call malloc, it's just going to use the same page that was already allocated, and it's going to start filling it in the same way that we would have with our file system blocks. Yeah. If it's not fully filled and I want more, I'll just keep writing into the same block until I run out of space in that block, and then I'll move to another one and allocate a new one. Yeah. All right. Okay. So I think the one last place I want to take us here is here. This maps file, recall, is what our operating system is telling us about the address space that we've got. And one thing I want to point out to you pretty quickly here is that all of these mappings here and all of these ranges that we've got in the address space, these are page aligned. If you remember when we were talking about file systems and you were all watching me with glassy-eyed faces stepping through ext2 with hexdump, and I offhandedly said, oh, it's convenient that 4096 is 1000 hex. These are all 1000 hex based offsets. They're not not all 1000 offsets, but they are all relative to 1000. They all end with 000 because these are all page aligned offsets. And that is part of the reason why when you are working with your heap and malloc, you will sometimes be able to go past the end of what you have requested for allocation with malloc because the entire page has been allocated for your process. But once you get past the end of the page, that's when you get faults. That's when your segmentation fault is usually going to show up, is when you go past the end of the page that's been allocated for you. All right. At this point, you should be able to virtual memory. You should be able to do lots of stuff with virtual memory. The idea of paging really does solve the problems that we had with segmentation, but it introduces its own new problems. Page directories effectively take the same solution to the problems that we had with paging and with segmentation, and it applies it to paging itself, and thus solves the problems that we were having with paging. Now we only have to allocate as much as we actually need for this thing. All right, with that, what I would like to do is switch back over here to Mentimeter, and I'll give you a moment to join, but I have some review questions if you want to follow along with me with what time we have left in the class today. So I've tried to go back to some of the initial parts of our course to prepare some of these questions, and I'll give you about 30 more seconds to join up. All right. Okay, awesome. Yeah. For me, the biggest difference between these two things is just one is using this inode structure and the other isn't. The other is like embedding metadata for files all over the file system as opposed to right up at the beginning. Clusters versus blocks, this is a fair thing, but I'm going to say that these are effectively the same ideas. Blocks in VSFS and ext2 do go all the way back to the top of our volume, whereas with clusters, we're only dealing with clusters in the cluster heap, and prior to that, we're using sectors. But these are effectively the same idea to me. This one, when I started thinking about these file systems a couple years ago, I was kind of surprised by this, that the directory structure relationship and the file name relationship are effectively the same across both of these different file systems. Both VSFS and ext2 have, and exFAT have allocation structures. exFAT has an allocation bitmap that is used for cluster allocation, whereas VSFS and ext2 have two different allocation structures, but they still use allocation structures for these things. And then superblock versus MBR, these are effectively the same concept to me. Okay, we get it. Do you have any questions for me about file systems before I move to the next question? I'll give you 5 seconds. There will be another question for questions area. Okay, I'm going to go to the next question. This next question is going to start to be about interprocess communication. Okay, awesome. Yeah, it's a queue. It's a queue underneath. So in this course, we've seen 3 data structures effectively. We've seen linked lists, we've seen queues, and we sort of saw trees, maybe, if you squint at file systems and think about them as trees, but we didn't actually implement anything that was tree-based. So we saw lists and queues. Those were the data structures that we saw in this course. A pipe is effectively a queue structure, where writing to it is enqueuing data and reading from it is dequeuing data. Here's some code. I want you to study this for a moment. And the question that I'm going to ask you is, why does this code block? I will give you 10 seconds to read this code and think about it. Okay, do we have an idea? Okay, I'm going to go to the next slide, which is actually asking the question. This is a terrible way to ask this question. I'm sorry. I should actually have the code up on the screen when I'm asking the question about this. Give me a moment and I will do that. Please forgive me. I'm even in the right directory. Okay, here is our code. The important part is really kind of over here where we're doing this stuff here. So the answers here, forgive me again. The answers here that I've got is that the right end of the pipe is not closed by the child. So remember that the read operation on a pipe here in our child process is going to block if there's anyone that could write to the pipe. If there's anyone that could possibly enqueue data to this queue, it's going to wait for that thing to possibly queue data to the queue. There are 2 processes that are running here that have ends to this pipe open. The right end of the pipe is open in the parent process. That's outside of this loop or this conditional statement that we've got here. Data is written to it, and then we're waiting for the child without closing it. We have to close it in the parent to indicate to the child there's no data that is ever going to come from me after this. I'm finished writing to this thing. The child will also block itself if it has the right end open. It's going to get stuck waiting for itself to write data to the pipe, but it can't write data to the pipe because it's currently reading on the read end of this pipe. All right. Transit hater. I like that transit hater and bike enjoyer are temporarily at the top here and then getting shoved down, but they're stuck next to each other. Okay. I'm going to skip past this and I'm just going to go to more questions. And I'm just going to open this code up in my terminal here. And I'm going to give you a couple seconds to take a look at it. And then I'm going to try to do some rapid switching between my terminal and Mentimeter so that I can have the code up at the same time as the question here. I'll give you 10 more seconds to take a look at this code. And the question ultimately is, does this contain a critical section? Okay, I'm going to pop over to my Mentimeter slides. I'm going to start the quiz, and then I'm going to put the code back up. All right. So yeah, this code does contain a critical section. If this code were run concurrently, so thread remove next were run concurrently, this line right here, line number 8, is a critical section. This is a single assignment statement, but this consists of many loads. This is many different loads. We have to load remove next. We have to load remove next, and next, the next, the next, the next, the next, the next. We have to load all these nodes and all these links, and there's going to be at least 3 instructions here to do all of these loads. Then we have to do a load of this, and then we have to do a store. So for this one line of code, there's like 5 different instructions. And if we're interrupted at any point in between these, we can get into a situation where we will unintentionally lose nodes or unintentionally get into a state where we are going to be referring to null. All right. Let's do one more question, and then I'll show you my comic. There are multiple answers for this one, so choose multiple things. All right, okay, so total ordering is definitely not a condition for deadlock. It's a solution to deadlock. It will allow us to make sure that we can guarantee that code will not deadlock. Locks are not a condition for deadlock. This code deadlocks. It deadlocks. Now, there are arguably locks underneath this code that exist, but the lock itself is not a requirement for deadlock. Mutual exclusion is a requirement for deadlock, but the lock itself is not a requirement for deadlock. All right, I'm going to post a link to these slides, the complete set of slides, so not just the ones that we got through today, up to the course webpage. So you can find those up on the course webpage after class. That's it for today. I hope that you all have a great rest of your summer after the exam. Good luck in your courses if you continue to take courses after this one in the summer. And then maybe I'll see you in the fall after the final exam. Bye, everyone.